Okay, so this last screencast for chapter 4, reactions in aqueous solution, is going to deal with a type of reaction known as an oxidation-reduction reaction, which is very simply a reaction that involves the transfer of electrons from one substance to another. So the driving force behind this type of reaction is that transfer of high energy electrons. So a really common form of a redox reaction is when metals corrode at their surface with moisture in the air. So copper, for instance, will form this green coating. Iron, will rust, and other metals will form different types of coatings at their surface. So what's really happening, though, is the solid metal. So in this case, we have an example of a synthesis redox reaction. Calcium plus oxygen makes calcium oxide. And at the surface, you have electrons being pushed away or grabbed, really, by the oxygen molecules here that are in the air. So the calcium is losing electrons, so it's being oxidized, and the oxygen is gaining electrons and becoming the oxide ion that you see up here as part of the calcium oxide compound. So at the surface, you have the new compound forming, and it looks different from the surface of calcium. And then at the same time that calcium is oxidized, oxygen has to be reduced, which is when the oxygen gains the electrons. So you have to have both oxidation and reduction occurring at the same time. And there's a couple of acronyms that you might use one of to help remember what's happening with oxidation and reduction. So the first acronym is OIL-RIG. OIL stands for oxidation is loss of electrons. RIG stands for reduction is gain of electrons. So that's OIL-RIG. The other acronym that might work better for you is LEO, the lion, says GER. So LEO-GER. LEO stands for loss of electrons is oxidation, and GER stands for gain of electrons is reduction. So in order to be able to follow what's happening with the electrons, it's important to be able to assign an oxidation number to each element in the reaction. Also, you might also see the term oxidation state. And so think of the oxidation number as a hypothetical charge. It's an artificial division of electrons among the atoms, but it gives us a way of following the electrons through the reaction. And these rules we've seen before. I made them part of the summer assignment, and we talked about them prior to that first test. So this should be a bit of a review, but I want you to paraphrase these 6 rules for assigning oxidation numbers to elements in oxidation-reduction reactions. Again, don't write every single word here. Abbreviate, paraphrase, do whatever you need to do, but these 6 rules you guys need to know in order to successfully follow and complete redox reactions. Okay, so here's just a quick practice example of assigning oxidation numbers within a compound. Okay, so we have 2 different compounds here, potassium permanganate, which is purple, and potassium manganate, which is green. And based on the rules that you just looked at prior to this, you should be able to figure out what the charge is on the manganese atom in each of these compounds. So let's start with potassium permanganate. So you can take a look and try and do it by yourself, or you can just copy my solution down. But you'll see here we have potassium is always +1, oxygen is always -2. And you take into account how many of those atoms are in the compound. And that leaves you with 1 unknown, because everything has to add up to 0. This is a neutral compound. So when you fill in the multiplication and then solve for that number, x, you end up with an oxidation number of +7 for manganese. One thing to remember about metals is they're always going to be positive in their oxidation state. And then if we look at the manganate ion in potassium manganate, again, we have potassium is +1, but there's 2 of them this time because the manganate ion is actually a -2 ion. Oxygen is the same, -2 for each atom, and there's 4 of them. So then when you fill in the math and solve, because everything has to add up to 0 in this compound, you end up with an oxidation state of +6 for manganese. So it's different than it was in the previous compound. Okay, so here's another example, the dichromate ion, which is a total charge of -2. What is the charge, or sorry, what's the oxidation number of chromium? Okay, so again, you fill in what you know. You know that you have 2 chromium atoms, that's like 2x. You know that you have 7 oxygen atoms, and each one is a -2 oxidation state. And all of that has to add up to a -2 because this is a polyatomic ion with a 2- charge. So when you fill in the math, you end up with 2 chromium atoms having a charge of +12, which means each one has a charge of +6. All right, so there's 3 main types of redox reactions. There's the synthesis reaction or combination reaction, like you saw at the beginning of the presentation. There's decomposition reactions, so a single compound breaking down into 2 or more. There's also combustion reactions. Combustion are actually a really important type of redox reactions, but we're not going to talk about combustion reactions in this chapter. And then there's the displacement reactions, which are the ones that occur primarily in solution. So those will be the ones that we're going to focus on in this chapter. And there's actually, you can break them down into hydrogen displacement, metal displacement, or halogen displacement. So if you look at what's happening in this displacement reaction, this is a hydrogen displacement reaction because it's a metal, magnesium, reacting with hydrochloric acid solution. So the hydrogen is going to get displaced in this case. So when you look at the activity series, which is on page 134 in your textbook, find hydrogen, the hydrogen ion in the series, and look to see that magnesium is above hydrogen in the activity series. So any substance that's above another substance will be oxidized by that ion. So we have the hydrogen ion, and because it's below magnesium, it will oxidize magnesium in this reaction. So here we have what's happening at the macro level, a ribbon of magnesium and a solution of hydrochloric acid. And here's what's happening at the atomic level. Remember, hydrochloric acid is a strong acid and a strong electrolyte. So it's 100% ionized in solution to the hydrogen and the chloride ion. Magnesium is a solid at the beginning of the reaction, so it's drawn as a solid here as the gray circles. When the reaction starts, it happens at the surface. The electrons are leaving the magnesium and going to the hydrogen ion. So that causes it to form these little diatomic molecules of hydrogen. So you'll see that as a gas bubbling up through the solution. What magnesium then does is becomes a +2 ion. It's the magnesium chloride compound, but they're both ionized. It's an ionic salt, so it's completely ionized in solution. So what you have, you still have chloride ions on both sides of the equation. So you can see that that would be a spectator ion in this net ionic equation. But the magnesium is oxidized, the hydrogen is reduced, and the chloride doesn't change. Here's another metal displacement reaction. In this reaction, we have silver as the ion, and it's part of the silver nitrate compound, but in the net ionic equation, you're going to see that that's the spectator ion. So we have the silver ion and we have copper metal. So find silver on the activity series and make sure that it's below copper. The silver is below copper on the activity series, which it is. So that means that the silver ion will oxidize copper. So the silver ion is going to gain the electrons, copper will lose the electrons and be oxidized. It forms the compound copper 2 nitrate, completely soluble in solution. So it will be ionized. And then the silver, you can see here, it actually deposits right on the surface of the copper as it's coming out of solution. So at the surface of the copper wire, you actually have little silver atoms building up. And notice the solution turns blue. So when copper is oxidized, it actually changes color and makes the solution blue. Okay, so copper goes from an oxidation state of 0 to +2. So it's becoming more positive, which means it's being oxidized. Silver goes from +1 to 0. So it's gaining the electrons, becoming more negative, and being reduced. However, because silver is below copper on the activity series, the copper ion will not oxidize the metal silver. So the reverse reaction does not happen. Okay, so here's another image of the activity series. We were just looking at silver and magnesium. Silver and copper. So silver is here, copper's here. And silver, when it's when a metal is below another metal on the activity series, the ion of that metal will oxidize the solid metal above it, which means the reaction will take place. So here's another problem. Will an aqueous solution of iron 2 chloride oxidize magnesium metal? Okay, so let's go back one slide. Magnesium metal is here. Iron 2 or iron is here. So the ion of iron is below magnesium. That means the iron 2 ion will oxidize magnesium. So this reaction will take place. All right, so we're going to write the balanced molecular and net ionic equations for the reaction. So here's magnesium plus iron 2 chloride. It's a displacement reaction, right? So the magnesium displaces the iron, and you get solid iron and magnesium chloride. And the charge, if you follow the oxidation numbers, magnesium goes from 0 to +2, so that's oxidized because it had to lose 2 electrons to become an ion. And iron goes from +2 to 0, so the only way it can become 0 is that it gained 2 electrons from the magnesium. So that's the reduced species in this case. So another way to think about redox reactions, and it's often convenient to look at half reactions, is each half reaction for a redox equation. But the first step is the same. We're still going to write the molecular and net ionic equations for a reaction. So we have a reaction of a solution of aluminum nitrate reacting with solid magnesium. So if you remember from the activity series, or you can look again, but the activity series has aluminum below magnesium, so the ion of aluminum will oxidize magnesium. So this reaction will take place. So when we think about the displacement of aluminum out of the compound, magnesium takes the place of aluminum. So you get magnesium nitrate as a product and solid aluminum metal. If you look at the ionic equation, the strong electrolytes are completely ionized, and then the spectator ions are going to be canceled out. Nitrate gets canceled out, so we're left with the net ionic equation here. And you'll see if you follow the oxidation numbers, aluminum goes from +3 to 0, so sure enough, it's reduced. The magnesium we said was going to be oxidized, and it's going from 0 to +2, so it's becoming more positive. It's losing electrons, and it's being oxidized. So let's look at each half reaction. Okay, again, here's the net ionic equation, and there are the oxidation states for each element in the net ionic equation. Okay, so the oxidation number of aluminum changes from +3 to 0 on either side of the equation, which means it is being reduced. It's gaining electrons. So that half reaction, the only difference is with a half reaction is we actually show the electrons in the half reaction. So aluminum, 2 aluminum ions gain 6 electrons to become 2 aluminum atoms. Notice how -6 and -6 on the electrons and +6 on the aluminum ions add up to 0. We also have 0 on the right, so that's an important thing to remember to balance the charge left and right. So if we look at the other half of this net ionic equation, the oxidation half reaction, we're going to be focusing on the magnesium this time because it goes from an oxidation state of 0 to +2. It becomes more positive, and so it is oxidized. It's lost electrons. So the half reaction would look like this for the oxidation of magnesium. So this time we start with 3 magnesium atoms, and they become 3 magnesium ions by giving up 6 electrons, so that the 6 electrons are a product in the oxidation half reaction. Again, +6 plus -6 equals 0, and that matches the net charge on the left, which is also 0. All right. And if you add the half reactions back together, there's the oxidation half reaction, there's the reduction half reaction. You end up with, cancel out the electrons because they occur on both sides of the equation. You end up with the net ionic equation again that we started with. All right, so that's all we're going to do for tonight. We'll do a lot more practice problems with writing the equations out in class tomorrow.